dia. Hello, I'm Kim Serradell. I come from Meteomatics, a Swiss company. And first of all, thank you very much to the organization for inviting me. I've been in different editions as attending to the conference, and it's really a pleasure now to be presenting. Two first disclaimers: there is no traces of quantum computing in my presentation. It's a little bit more modest. And after seeing Petrobras, we are a smaller company. I will only discuss about and present one machine. You will see, and my subtitle, it's this, we are a weather information company, and some lessons learned and things that I would have known before when deploying an HPC. You will see that probably I will not explain fancy things, but I will explain my journey that led to have our own machine, and so in this last month. So first, I will more or less explain who we are and what we do at Meteomatics. I will talk about our weather model. We have an in-house weather model called Euro 1K. Then the deployment and the lessons learned when you deploy an HPC, an in-house HPC, and why we moved to an in-house HPC. Some next steps. We are now in production, but the job is not done. And finally, some conclusions. So usually I don't like to speak about myself, but I think that in this case it's important to explain a little bit the journey. I'm a computer scientist. I've been 14 years in Barcelona Supercomputing Center, as some people that there is in the room. I was leading the computational earth sciences group, and last year, finally, for different reasons, I decided to quit. And I changed, I moved to Meteomatics, and it was a big change in the sense that I moved from research to industry, from a non-remote work to a totally almost 100% remote work. And something important that up to now, as HPC, I upgraded, and I became more than a user. I think I've been using a lot of machines, but now in the next month, I discovered many, many things. So to explain a little bit about who we are, Meteomatics, we are a world-class meteorological and data science company. Our main business is the global, it's the weather intelligence. That means that we provide accurate weather data for any location at any time in any format to our customers. So if you come and you want this kind of data in the way that to plug it into your workflows, we can design it for you. We are more than 80 people based in Swiss, and we are working for all over the world. We work for different companies, different workloads. So if you are interested in weather data, I'm not the salesman, but I can forward you to our strong sales division. So what we do exactly, as I was telling, we have the main component is a weather API. We deliver a very performant weather API that can deliver the data as I was telling, from different models, but also the model that we have in-house. Then, very important, the weather model. This is the point. We are running our own Euro 1K model, also smaller ones, but now the king of the crown, it's the Euro 1K. We are also providing, based on those data, we are also providing solutions of map and visualization. Very important when you have all this data that you can have a very nice GUI to discover and to consult and information. And finally, something that I think it's quite fancy, but it's not really related, but we like to talk. We are leaders in developing meteo drones. Meteo drones are drones that are specialized to go up to the atmosphere and take meteorological data. And this is quite important in the sense that you will see that we use part of this data in a part of the atmosphere that is usually there are less, it's scarce in observations. We are ingesting to our model to improve the initial conditions and to improve the performance and the skills of the model. So here you have a caption of Euro 1K. Euro 1K, it's I will explain later, but it's the model running or the definition of the model is over Europe, and we are running at 1K. We consider that high resolution is the way of the best approaching some of the forecasting problems that we have and to provide better information to our customers. So here you have a capture of, I think it's cloud with with precipitation. I'm not a meteorologist myself, so I have struggled a little bit to when it's on Meteorologica, but yeah, after the years, you more or less to try to understand what you are showing. We are doing, you will see here, you see the full domain. It's a domain over Europe and North Africa. And here, where things start to be complicated, we're doing 24 runs per day. So that means that each hour, I'll explain later, we are doing a run. So that's why you'll see that we need HPC. We are integrating, as I was telling you, those models are very important, the initial conditions where the simulation starts. So as better initial conditions are, better should be your forecast. So we are using part of this drone data to create those initial conditions. Working at 1 kilometer, it's a grid that approximately 20 million grid points. And very important also for later is that we are doing 20 minutes output simulation. That means that we are generating lots of outputs. And you will see that this can be an issue when working with HPC. We are now at 80 vertical levels, depending on the configuration, and also very important for the quality of the simulation, we're using the IFS outputs from ECMWF, from the European Center of Medium Weather Forecast, to start with the boundary conditions. And finally, I promise is the last one on meteorology, and we jump to HPC. If you can, this is a little bit the comparison on what it's more on the best practice and what ECMWF delivers, that you can see that there is a big difference between the 7-9 kilometers that right now is the IFS product, with our spatial resolution that it's 1 kilometer. Very important, the resolution. If you want to track, for example, for people doing things on renewable energies like wind, it's very important to have a shorter time resolution. And yeah, the withdrawal is that we are very interested in the short-term forecast, and that's why we are providing up to between 24 and 48 hours. And now we move to why we need high-performance computing. I think you can imagine why, because these simulations are not done alone, so we need a tool to do it. So this is our workflow. The production workflow starts when discussing or talking on models. We start with the HPC, where we run those Euro 1K simulations. We do strong post-processing. We need to gather all the data. We need to process and reduce to what we are interested in. Meteorological models can deliver lots of parameters that not always are needed and interesting in our problem. We have fetchers. So our data center is in Germany, in Luxwaffen, and we have another data center where we have all our infrastructure. So we need to move all this data, and when we are talking about terabytes of information, this can be a problem. We ingest this data to our API, and then in the API, we are delivering Euro 1K to our customers. This workflow is really critical to be really on time, because usually when you deliver a weather forecast, you cannot afford to delay your final result 6 hours later, because then the forecast is not valid anymore. So we need to put a lot of effort to do all these things as fast as possible. So Euro 1K is a weather forecasting code written in Fortran. Yes, Fortran, we still in Earth Sciences, it's Fortran everywhere. I finished my degree, my bachelor in La Facultad de Informática without touching a line of Fortran, and now everything is in Fortran, and I think it will stay longer Fortran, so larga vida Fortran. It's MPI and MPI plus MP parallelization, depending on the configuration we work on both. I skip it here, but we are not using GPUs. Earth Sciences codes are really struggling to move to GPUs, I think a little bit as the reservoirs that Felipe told later. It's quite memory bound, so there are a few of them, and for example, our colleagues at CSC they have Cosmo. They did a very nice investment moving and with rewriting from scratch a model to port to GPUs. It's not our case. This is really a strong investment to do such a project like this. We cannot afford. And we are more or less the case of Euro 1K is running approximately in 37,000 cores. And we are producing 650 gigabytes per run, but we have 24 runs a day. So in fact, we run each hour, so the machine is never stopping. It's streaming data, so we need to take the data, post-process, remove it, and work in this model. So, and as I was telling, we have really strong time constraints where a simulation that should not run more than 50 minutes to have a little bit of time for the pre-process and post-process and to continue and to jump another one. So the production workflow, you see here the workflow I come from a user perspective, and you will see that workflows for us are really important, how we run, because we are running 24 simulations in a cycling, what we call rapid refresh, so we need something that orchestrates all this workflow. Yesterday, you have a nice example with the guys from Covalescent that shows a nice tool, very important. I will talk later. And as I was saying, very important, in less than 2 hours, we need to, since we start the simulation, as we ingest to API. So it appeared during the presentation, and in our case, we did a little bit the other way around. We thought at the beginning that cloud could be the solution. And we said, okay, let's move to the cloud. And last year, in 2022, we did a first proof of concept. Oh, they did. I was not there at that time, but they did a first proof of concept. And cloud was really a successful experience with a reduced number of nodes. They said the model is working, so let's go to the cloud. And then in summer 22, there is a first attempt to move the production, so this big Euro 1K to the cloud. And here, I don't want to be really strong words, but we had many issues to work this rapid update workflow. We were not able. Lots of issues, more than the technical, something that I was quite surprised, and we can discuss, and I think different cloud providers will have a different view. But in our case, we struggled to have this high number of nodes each time that we needed. So when we wanted to submit to launch, and this idea of providing virtual or resources was not appearing, and then, as I told you, if you don't get the resources at the time that you need, everything gets delayed, and it's really dramatic for us. So we took 2 decisions, a degraded workflow. That means that we continue the production, but really with less runs per day to cope with these problems. And finally, we decided to buy our own HPC. In this case, a tender was open. NEC, the Japanese company, but the subsidiary from Germany won the tender. And then I joined to Meteomatics. And yeah, I arrived there. You need to deploy an HPC. And I was completely, okay, I was user. And I said, okay, very confident. I said, no problem, I will do it. But yeah, when they put the responsibility, it's not, at the beginning, it was quite a challenge. But I said, I can do it. And you will see that now the rest of the presentation is all the things that I learned. And first of all, the most important is I was totally unaware of many things. So when you are, even if you are a strong user, and at the time at Earth Sciences department, we were strong users, but you are totally unaware of many things. I really empathize with people, for example, from operations, from BSc, because as user, you don't take care of things like the delivery times, networking on security. I learned a lot on networking of connecting different sites and lines that for me, network, it was strong protocols and strange protocols that I was not aware. So you learn. Burning test, I could have an imagine of what was a burning test to deliver a machine, but not how long they should run. The deployment tools that we have, each company, I assume that they have they own deployment tools. NEC has one LX3 Cineo software that has their own, but I think you are aware and you need to work with them. And many other things that you are not aware, and at the end, very important, all these things have an impact on the schedule. So when you try to say, we will go to production to that day, all these things can have different issues and delay this move to production, so you need to take care. In our case, we started the hardware deployment in January, beginning just after New Year's Eve, and more or less in mid-February, we had the first access to the early access to the cloud. Very short to which kind of cluster we are. It's I would say, small, medium machine. We have 300 nodes. our HPL, more or less, we are at 1 petaflop. We don't have a very big storage because we are moving data quite fast, so we don't need a very big one. We need a very performant one, but not a one. High performance network, we have an OPA. This is, and with the next talk from Cornelis, I'm really interested to see what they present, because you will see that, and the question that I did to Miguel previously, that we really depend on the network of the machine. So first, and here this is a special slide for the guys of EasyBuild. I don't know if you know EasyBuild, which is a software developed at the University of Ghent, led by Kenneth Hoste, and it's really a very nice tool to deploy software. So you cannot realize, I don't know if you are users, but you cannot realize the time that you can really shrink the time from that you receive and you say you enter the first time to the login node until you can start running things. With EasyBuild, okay, I'm a proficient user of EasyBuild, but in more or less 1 day and a half, our software stack was deployed. So, and then you have extra things really important in this deployment stage. You have combinations of tool chains. If you are a little bit more on ease on the software, you can do very nice combinations. Most of usual dependencies, Earth Sciences communities really cover it in EasyBuild, but also communities, for example, bio and so on. Modules are automatically generated, so that means that everything it's doing automatically, and there is reduced human intervention that can lead to failures, and you can recreate the stack if needed. This is really important in the sense that also one learn that you have when you deploy an HPC, you can have issues, and you will need probably to repeat things. So as much as things are automated, less time you doing tedious, because the first time can be nice, but the second starts to be, and if they told you a third time that they need to reinstall the file system at the end, if it's not automated, it's really dramatic. And also, this is, I never said that, but domain scientists should not deploy software stacks. This should be done by sysadmins, and then we deliver the software stack, and they work with their model, then compiling and so on. But I think it's the way to do it to get the best performance in the machine. Then very important, a workflow manager. So complex workflows cannot be done with a script, and sometimes I think most of you saw scripts in Python or Bash that are really 1,000 lines of codes, and to manage dependencies is really dramatic. So invest, look for, when you are porting to your application, look for tools on your domain. There are lots of them for Earth Sciences, AutoSubmit, Silk, many of them. If not, you can create your own. We created, in this case, there was a prototype in the company, so we continued to the prototype. And you will see that it reduces the deployment time, and it simplifies the production of operations in the sense that you can deliver then when it's in production, you can deliver the application to someone else to operate it without having really the knowledge. And something interesting, if you want to, okay, you have duties at Meteomatics, but if you want to live better, is if you can strong and invest in auto-recover features, in the sense that if your workflow is able to detect when a job failed, can really resubmit it. If something is stalled because many other things, can kill himself and really restart it, this will make your life much more easier. Acceptance test, I was not really aware. I knew that there were, so work on the synthetic benchmarks. Synthetic benchmarks, vendors, I think you have it much more, it's more known, but when you need to, in this case, the one advantage for us is that we had this machine was only for an application. For example, I think on things like at BSc, that Mare Nostrum, there will probably 100 different applications, and more or less you need to do it for all of them. In our case, we had only one application, and it needs to run one application. This is very good. But the vendor doesn't know about your application. So you need to give clear instructions, which is the case, which is the result, because probably there will be working parallel. So you will be working, but the vendor, in order to accept, that will continue working in the machine. So, and to avoid going lots of communications, which is the benchmark result, deliver this. So from the beginning, you have a folder with all the compilation, so on, results, and what should be. And I was saying, with thanks to EasyBuild, if you need to test different toolchains and so on, this is really much more easier. And if you are having, for example, testing different MPI implementations, it's really, really interesting to have such a tool. And something that really appeared, and this was really a nightmare, the biggest nightmare is the input and output learning. It's the think on I/O. Not everything is computation. We have a GPFS, and it's not really easy to work on with such a file system. And when we arrived, we got very good times from the beginning computation, but not for I/O. And we struggled a lot, and then you start learning about NPI I/O things, Romeo hints, parallel net CDF, asynchronous I/O. And in fact, it took us more than 2 weeks to really have the machine, the model, with the result that we wanted. And we finally ended up to really modifying our source code to really make it work as we wanted. I/O is not really easy to profile. Tested tools like Darshan, but that was not really easy. I rely a lot with benchmarks, BTIO. If you are using parallel net CDF, it's really, really a good benchmark to test how your file system is going. And then a bonus track when you are transferring big amount of data, rsync and SCP is not efficient, so you need to go to other alternatives. And you have there things like BBCP or endpoints to really to make the stream of data really, really fast. And what's next? Now that we are in production, we have lots of things to do. We need to prepare for the operational activity. We need to deploy monitor tools, testing. For example, the idea reframe at CSCS is really an interesting tool. We need to deploy CDCI for our developers. And also that I learned is that nodes have minor failures, but memory have problems, and sometimes nodes are failing. And when you have a machine of 300 nodes, if you lose one node, it's not. If you have 6,000 like BSC, it's not a problem. With 300 can be. Tools like the NHC from National Berkeley Laboratory is very interesting, removing nodes from Slurm to avoid that your simulation. Invest on monitoring. We did this very nice integration. It was already there, but we did it Elastic and Slurm, and then you can see, and this is our workflow, and when everything is green, everybody is happy. And also, I come from BSC, so I need to put a trace. This is a trace from Paraver, from an execution, but this is a trace of 4 nodes. If you want to go to trace a full-scale run of such a volume, tools are having lots of problems. Right now, I'm still not able. I did not put many time, but Extrai cannot really. Extrai hangs when trying to trace the full production 37,000 cores. We need to test other compilers, the compiler of AMD, fabrics like the OPX, and improve the I/O. And I think, the last point is that if you are interested on all these things in Meteo, you can join us. We have in my team 3 positions open. And this is last learning, not new, but I'm always that machines are important. The iron is important, but beside the machine, in front of the machine, there's always a human. So please take care of your employees and people working next to machines. And that's it. This is a summary of the lessons learned. Thank you very much. And yeah.
Thank you so much. It's really, thanks for this talk. It's really interesting. I can see a talk as if it's done by CSCS, most of the stuff. So I have like couple of comments. So EasyBuild, we have been using it a lot, and we have been part of the development, I believe. And maybe Victor.
Yeah.
What about SPAC? Have you ever tried it?
Yeah, I tried it, and at that time when I was in the Center of Excellence of Weather and Climate, EasyWays, we did a comparison. And at the end, I think both are quite interesting. And I would say that finally, for historical reasons and for for the two colleagues and a former HPC now employee, Oriol Mula, we decided to stay with EasyBuild.
Which makes
Yeah.
sense, yeah.
So, but SPAC is really valid as well, but we stayed, and now I'm EasyBuild. I could change, but yeah, it could.
The second part has to do with the climate code. I have seen that, you know, Meteoswiss have interest in Kubernetes.
Yeah.
And some of it just related to AI, and maybe that could be, I don't know if you have taken that in consideration and see how what's what we're running.
No, I would say not in HPC. We are considering Kubernetes in our infrastructure for parts of the workflow that we have, mainly with the API. We are starting to really go to that direction, but on HPC we are not. We are staying. We want to really focus and to stabilize this solution. It's only we are in production only from more or less 2 months ago, so we need to, but not on HPC. Go.
Yeah, I've seen also Reframe, and I was not sure if you are using it or it's.
I want to use it. Okay. I want to automatize because tests right now are manuals. And I've been, I think, in 2 or 3 presentations. Again, in the last EasyBuild user meeting, they presented Reframe, and I want to deploy Reframe to really automatize testing.
We have it like in every time some nodes will be marked as down or they have like bad behavior, we rerun Reframe on them. And that's including all the benchmarks that you mentioned. There are more than that, actually. And then we say, OK, they hit the threshold based on the Reframe, and you can see all the numbers expected from them. That's including GPU, including HP, and then that's what bring it to production.
It's exactly what I want to do. Right now, I'm doing it manually. I do a small case of the Euro 1K. I run the BTIO. I want different ones, but I want to automatize, and for this Reframe. So this summer, probably, that the activity will be a little bit. I will deploy the Reframe. Yeah.
Thank you.
Instance.
Okay, another question that's from me. So I was wondering if you can explain it a bit, the workflow that you have for getting the data from the Meteor drones into your HPC. It's fully automatized. It's a manual intervention.
Yes, from Meteor drones. I'm not really an expert on this because it's the drone division, but when we sold Meteor drones, we sold what it's called a Meteor base. So it's a box inside with the drone. So the box opens and the drone goes and comes back to the base. In this base, we have a connection, and this connection connects to the API, delivers all this data to our API. This data is stored in what we call our caches. And then when we start a simulation, a Euro 1K, we connect to our own API, and we retrieve this data, and we create the initial conditions based on.
Do you operate on Southern Hemisphere as well?
No, right now we have bases in Switzerland, and we have the first international base is now in USA. We have in North Dakota, we put one base there.
So the input files, I know that there are many for Cosmos. They're getting some input files from UK, and there are different sites that deliver these numbers. And that's what these input files include. I mean, pressure, temperature, different.
You need to create the initial conditions on this model, and you can use You can use whether, for example, the GFS, which is the American, which is free, this one, or you can go to other or create your own ones, as we do. We do a mix with the ones from ECMWF and from our drones, and also radar assimilation is really important, so we put it inside. And here you have a mix of parameters. You need all the ones that you're saying. You need also, for example, to put the topography. You need to put the land use. You need to put many things that will be the initial state, and then also in the next steps of the model, there will be also this information needed for the model to compute to resolve the equations.
Would 1 kilometer resolution be the highest, or are you expecting to go beyond that? Because we know that there are like topologies in Switzerland where we have the distance. It's really too narrow, and that's different in condition.
I'm not really a meteorologist, and here for this question, I think it's more on the modeler's team. but you can go, and there are models going to the scale of the sub-kilometer, but then also the physics and all the parameterizations that you have inside your model needs to be adjusted. So in our case, we are better than going under the 1 kilometer. What we would like, and this is a strong, challenging problem, is to do a bigger model, a bigger domain. So try to cover more things, and hopefully it would be nice to cover the whole world with. But then you can imagine that all these problems are exploding, and only the I/O to manage this, it's overwhelming. So this is, by the way, all the Destination Earth program from the Commission is what they are going on this direction, really, to go to the max resolution.
For one more question.
Yeah.
It's interesting because it's a little bit similar with what we have in reservoir simulation. We have the past, and we are trying to predict the future. In our case, we always simulate also the past to try to adjust the models. You do that
yes,
as well?
we do hindcasting also. What we call hindcasting, we do. I think it's quite similar, our both activities, because in your previous comment, you were describing an ensemble simulation, the thing that you perturbate your different realizations, and then instead of having a deterministic, this one is a deterministic simulation, we run one, but it's really interesting to do what we call an ensemble, that you can do as much as possible depending on your computing. You deliver and you change the initial conditions, and then you will have a spread, because these are chaotic models and they will move. And finally, you can deliver forecasts based on probabilities.
And you are limited nowadays by the resources of HPC to reach that level.
Yes, this would be really nice to have, and we are not doing probably in the future, but when you do ensembles but for this, machine learning can solve and can give us a lot of, instead of 200 members and so on. That would be.
Okay, I think that there are more questions, but we have to stop here. We can use the coffee break for having all this discussion. Thank you again.
Thank you for the invitation.